An interesting take on simultaneous equations here, where we're finding the integer and fractional parts of different numbers. I'm just going to write the equations down again, but so they're lined up. So you can even see in each one we've got a part of x, part of y, and a part of z. I might just write the x here. I'm just changing the order slightly. Okay, now a really good approach when you get, say, an x in each one, and like basically like there is something appearing of each unknown in each one, is to just add them together. So let's do that. And the thing is, when you add these two together, you're going to get back to x because it's just the integer part plus the fractional part. That's going to take you back to x. And the same is true for all of them. So in fact, when we add them together, we get 2x plus 2y, because adding these two together gives us y, and adding these two together gives us x. So 2x plus 2y plus 2z is going to equal 7.8 plus 2, 9.8. And then we can either factorize out 2 and then divide by that 2, or just divide by 2 straight away. X plus y plus z is going to equal 4.9. Okay, so that's quite a nice little result. Removed all the fractional and integer parts. Okay, now we want to find out the integer part of y. What I did at this point was just start adding some of the equations together in pairs. And I actually picked the first two to begin with. But what ends up being really useful is, well, because I also did the first and the third, but it's really useful to add the second and the third. You'll see why in a second. Because when we add these two together, we're going to get x. Remember, we want to find the integer part of y. X plus y plus the fractional part of y plus the integer part of z plus z is going to equal 5.6. The thing is, we've just shown below that these three, no, not those, these three add together to give 4.9. So if I subtract this equation from both sides, like the left-hand side from the top, left-hand side, and the 4.9 from the 5.6, then I get the integer part of y plus the integer part of z equals 0.7. Oh, and this is amazing because it must be then that the integer part of z is 0 because we know that they're all greater than 0. It can't be negative, it can't be 0. And it follows, therefore, that the integer part of y is 0.7. And we're there. Let's say you didn't quite get that quickly. That's okay. If you went with, say, the first and the second parts, then we'd get x plus the integer part of x plus, sorry, that was the fractional part of x plus the integer part of y plus y plus z equals 7.8. And we could again subtract. So I'm just going to get rid of the x, the y, and the z, and then subtract 4.9, which would become 2.9. See, that's also very useful because it tells us that the integer part of y is going to be 2, and the fractional part of x is going to be 0.9. And then finally, we could look at the first and the third, add them together. So that would give us x plus the integer part of x plus y plus the fractional part of z plus z equals 6.2. Again, subtract, take away 6.2. Sorry, take away 4.9 from 6.2. That will be 1.3. And then I get the integer part of x must be 1 and the fractional part of z must be 0.3. And we could, if we wanted to, bring the whole solution together now. So y is going to have to be 2.7, formed by my integer and fractional parts. X is going to be 1.9, and z is simply going to be 0.3. If we add those together, you do get back to the 4.9. So that is our complete solution. And if you went off on those little tangents before you realized to do the second and the third, then fair enough, as long as we get there. But yeah, lovely question.